The last couple of lessons have been super boring and painful for me, so I needed a nice dark Canva presentation full of depression and angst to get us through. This is Vertical Stretches and Compressions, Unit 3, Lesson 9. Vertical stretching is when the graph of a function in the form of y equals k times f of x, where k is greater than 1, is a vertical stretch of y equals f of x by a factor of k. Think of stretching like stretching a rubber band, all right? And it goes up and down. Example number 1, use a table and a graph to show the vertical stretch of f of x is equal to 2x squared compared to its parent function f of x is equal to x squared. So first we're going to use a table to show this. So this is our parent function. We're going to go in order. We're going to go with our stretched function. Sorry, not translated. Our vertically stretched function first, which is this one right here. Why is it so fat? Oh my goodness. Grossy Josie. Oh, because I'm on the wrong tool. I'm doing great today. Okay. Let's change this to white. I'm going to have to cut all of this already. Okay. We're going to start with this formula over here on this table. So what you do is you take your x value, you plug it into the formula, and you solve, which is what we've been doing for weeks now. F of x is equal to 2 times our first x value, which is negative 2. I'm pulling that from the table here. And then we finish our formula, which is squared. So we do our parentheses first. Negative 2 times negative 2 is positive 4, so we end up with 2 times 4, which gives us 8. So our first value is 8 there. You would continue this pattern all the way down to get all of these values. If you need me to show you how to do that, please comment and I will do that. Okay, let's do this formula over here and we'll do this value as an example. So we have f of x is equal to our x value, which in this case is 1, squared. 1 times 1 is 1, so our f of x value is 1. You would follow this pattern to fill in all the values on this table, okay? You're going to end up with all of these values. Let's double check that I got it right. I said 8, they said 4. Look at me messing up. Let's see why they think it's 4. Let's see if I can agree with them or not. X squared is going to be 4 times 2 would be 8. They're delulu. I don't know why they think it's 4, but whatever. We'll just roll with it. Maybe I wrote the problem down wrong. So here's our values. Here's our graphs. You can see negative 2 and 4 is this point right here, okay? So they just graphed each of these points and then connected them to make these two parabolas. Note that the graph of the dilated function, which is this one, okay, is stretched. See, it got stretched, and when you stretch a rubber band, the sides get closer. That makes sense, right? So each of these points are farther away from the x-axis. So for example, when we're dealing with this point, negative 1, 1, you can see that at negative 1, it now becomes 2 on the y-axis. It got stretched further away. So it was here, and now it's up here. Okay, that's getting stretched further away. At negative 2, we were at 4, but now we're at 8. It's getting stretched. Oh, that's where it went wrong. I see now. I had it backwards. I had my two things switched. So 1, 1 should be over here, which it is, okay? And negative 2, 8 is over here. So they did the parent function on this side, and they did the dilated function over here. That's all that was. It makes sense now, okay? Each y-coordinate in the dilated table has been multiplied by 2. So these x-coordinates all stayed the same. This is the parent function. We just multiplied this by 2. So in the parent function, it was a 4, which you can see right here. And in the dilated function, it's an 8, which you can see right there, okay? The y-coordinates on the table got multiplied by 2. The x-coordinates stayed the same. Here's example number 2, and this is me hiding from algebra because algebra is awful. Use a table and a graph to show the vertical stretch of f of x is equal to 4 times the absolute value of x compared to the parent function f of x is equal to the absolute value of x. So this time we know that they want this to be the parent function, which is this one, and this table to be the dilated one. So we're going to go ahead and use this table for our parent function. We'll pick this number and do our formula. So we have f of x is equal to the absolute value of our x value, which is -1. Absolute value just means this is positive no matter what. So our answer there is 1. And we'll do this for our dilated version that's either been stretched or compressed. So we have f of x is equal to 4, which means it's being stretched like a rubber band, times our x value, which is 2, the absolute value of 2, which makes this just 4 times 2, which means that our coordinate over here is going to be 8. You would continue that process to fill in all of your points on both tables. I didn't fill in the tables, but you can see here that here is our parent function. You can tell because it's touching 0, 0. And here's our dilated function. It got stretched, and just like a rubber band, when you stretch it, the sides pull together and it gets taller. You can tell if you look here that if we look at this point of -1 on the x-axis, it's sitting at 1 on the y-axis. But when we go to -1 on our dilated function, okay, the y-axis is at 4. That's because each y number got multiplied by 4. Let me switch back to white so you can see what I'm doing. So here we see we have -2 and 2. So if this value is 2 and we multiply this by 4, then this value should be 8. And look, it is. You can see that right here. It's -2 and 8. Okay? So these y values are getting farther from the x, and the sides are getting closer together. It's getting stretched vertically. Okay? The y values, the x values all stay the same. The y values change. So again, let's pick another one. Let's go with -1 on here is +1. Okay? So if we multiply that by 4, because that's our rate of change, okay, 1 times 4 is 4. So over here we should have -1 and 4, and we do right there. Okay? Here's practice question 1. This is at the end of your lesson, so just write your answer down and you can enter it later. Complete the table to vertically stretch the parent function f of x is equal to x cubed by a factor of 3. Okay? So try to do this on your own, and then we'll work through it together. Pause the video. So we're just going to complete this. Okay, so we know that when x is 0, f of x is 0. Okay, here's our formula that we're dealing with, and that makes sense because if x is 0, 0 times 0 times 0 is still 0. So let's solve for 1. Okay, if we have f of x is equal to our new x value, which is 1 cubed, 1 times 1 times 1 is 1. Okay. If we have f of x equal to our next x value, which is 2, and we cube that, 2 times 2 is 4 times 2 is 8. So there's all of our values. Now it wants to know what goes right here. Okay? This is really easy. If this is our parent function, okay, which would be just f of x is equal to x cubed. What did we do? What did we change here? How did we get from just the parent function to our dilation? We multiplied everything by a cube root, right? So the number that goes right here, I'm doubting myself, but I feel like it should just be 1. Oh wait, but we're doing it. Oh, it's in this answer right here. Complete the table to vertically stretch the parent function by a factor of 3. It's not 1. It's by a factor of 3. So they want us to do it here. So I did all of this wrong. This is our parent function. These are our numbers for our parent function. We want to find it for this formula. So now everything's getting multiplied by 3, which makes sense because this would still be 0. 3 times 0 is 0. Okay. 3 times 1, it's not going to be 1 anymore, it's going to be 3. And 3 times 8, it's not going to be 8 anymore, it's going to be 24. Okay, So we filled out the table values for our parent function first. Then we got our new formula, our dilation formula. It told us to use a factor of 3. And we solved by sorry, by multiplying all of our values by a factor of 3. So 3 times 0 is still 0. 3 times 1 is 3. 3 times 8 is 24. If that didn't make sense, comment. I will make another video. Here's quick check question number 1. This is at the end of the lesson. I will not tell you the answer, but I will tell you how to get it. Which of the following tables shows that y equals k times f of x results in the parent function y equals the absolute value of x plus 4 being vertically stretched by a k factor of 3? Okay. This is going to take a little bit of thought, but I'm going to walk you through how you would do this. So this is our initial formula, and we're going to change it by a factor of 3. So first we need to write our new formula. Okay. So we have y equals, and we're multiplying everything by 3. Okay. And then we're going to put a parenthesis, and we have the absolute value of x plus 4. Okay. This is our new formula. Okay. What we need to do is we need to figure out our original table first for this formula. Okay, we have all of our x values. They're all the same, 0, 1, and 2. So if y equals the absolute value, our first x value is 0 plus 4. Okay, that's going to give us y equals 4. So our original table is going to be a 0, 4 for our first coordinate. Okay, this is the original table. So already we can tell that one of these tables is wrong because what we're looking for is this table. Okay, it's going to be different. So already one of these tables is eliminated. Let's figure out the coordinates for the next x value. Okay, so we take this formula, we go y equals the absolute value of our next x value is 1 plus 4. So 1 plus 4 is 5. The absolute value is 5. So our next coordinate point is going to be 1, 5. Okay. One of these tables, it looks like, is showing us the information for the parent function, for the initial function. Okay. Let's do the last one. Y is equal to the absolute value of our last x value plus 4, which gives us 6. So our last one is going to be 2, 6. Okay. So it cannot be this table. What we need to do is now do this formula. So which values are going to change? Is it the x values or the y values? And those values are going to be multiplied by 3. Okay. So one of these sets of numbers is going to stay the same. I wonder which one. And the other set of numbers on the table is going to be multiplied by 3. So write down, you can't write down table 1, 2, 3, or 4 because they shuffle these, but write down which table is correct so you can enter it when you get to the end of the lesson. Okay? Let's talk about vertical compressions. The graph of a function in the form y equals k times f of x, where k is between the values of 0 and 1, so it's a decimal or a fraction, is a vertical compression of y equals f of x by a factor of k. So when you're thinking of compression, think of squashing. Think of sitting on a whoopee cushion. You're flattening something out, so the sides are going to go wider. Okay? Here is example 3, and this is how algebra makes me feel. No! Cry, 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 sweat, sweat, sweat. Use a table and a graph to show the vertical compression of f of x equals 1/2 x cubed compared to its parent function, f of x is equal to x cubed. Now we know that this one is a compression because it has a fraction or a decimal in it. The thing that's different, that change, that factor, that k value, is less than 1 but greater than 0. So here we have our two tables. This will be our parent function, and this will be our dilated function. So let's figure out some of these answers. We'll start with this one for our parent function. So we have f of x is equal to our value for x, which is negative 2, cubed. So negative 2 times negative 2 is positive 4 times negative 2 is negative 8. Okay, we'll do the same value for our next equation, our next function, which is our dilation, which is this one right here. So now we have f of x is equal to 1/2 times our x value, which is negative 2, cubed. Now we have to do PEMDAS, order of operations. So first we start with parentheses and exponents. So we still have our 1/2. Negative 2 times negative 2 is positive 4 times negative 2 is negative 8. 1/2 times negative 8 can be the same as 8 divided by 2, okay, which is negative 4. You would continue this process down for both tables to get all of your values, okay? Here's all of your values. You would plot these as coordinate points, and you would get these graphs. Note that the graph of the dilated function, this is the original, this is the dilation. You can see that this one is fatter. It got sat on, it got squashed, okay? The dilated function is compressed such that for the same x value, the points are closer to the x-axis than they are in the parent function. So we've squashed it down, we're getting closer to this x-axis. For example, if we're sitting at negative 2 here, we're clear down at negative 8 on y. But here, negative 2, we're at negative 4 because we sat on it. We're pushing it closer. Okay? Each y coordinate in the table for the compressed function has been multiplied by 1/2, or divided by 2, compared to the y coordinates in the table for the parent function. So we took 8 and multiplied by 1/2 and got negative 4. We had negative 1 multiplied by 1/2 and ended up with negative 1/2. Okay. Here's example number 4, and oh my gosh, why are we still doing algebra? Use a table and a graph to show the vertical compression of f of x is equal to 1/2 times the cube root of x compared to its parent function, f of x is equal to the cube root of x. Because we have this fraction right here, we know that it's a compression. Fractions or decimals mean we're sitting on it, we're squashing it, we're making it fatter. Okay? So we have our two tables here. We'll start with our parent function, and we'll just go ahead with this negative 8. So we have f of x is equal to the cube root of negative 8, and the cube root of negative 8 is negative 2. Okay, let's solve for our dilation. So here's our formula for our dilation. We have f of x is equal to 1/2 times the cube root of our x value, which will go with negative 8 again. So we're going to deal with the square root first, the cube root, I apologize. So we have 1/2 times the cube root of negative 8 is negative 2. 1/2 times negative 2 is the same as dividing negative 2 by 2, is going to give us negative 1. You would follow this pattern for both tables and end up with these coordinate points. You would then graph these coordinate points and end up with these graphs. So the parent function, you can see, is taller, and this one is squashed. You sat on it, you compressed it. If you look at each of the points, like here, when we're at 1 on the x-axis, we're at 1. But when we've been compressed, we're only at 1/2 on the y-axis. Everything got divided by 2 or multiplied by 1/2, however you prefer to think about that. Okay. I don't know why I left that there. Ignore it. Question number 1. This is all you, and this is your introduction to Daddy Toast. This is still IN like we had from the last lesson, but he can like completely change the way he looks, and this makes my brain misfire, makes it fizz out like it's been tased or something. I can't handle Daddy Toast. IN is cute and adorable and smiley, and Daddy Toast scares me. Okay, and look at this. I went through twice and checked this to make sure that everything was perfect, and one of the formulas is gone. Okay, so we got the formula back. Use a table and a graph to show the vertical stretch of f of x is equal to 3x squared compared to its parent function f of x is equal to x squared. We know this is a stretch because our k number 3 is greater than 1. It's a whole number, so we're stretching. We're stretching up like a rubber band. All right. So pause the video, figure this out, come back, and we'll go over it. So here's all of your points that you should have. You have -2, -1, 0, 1, and 2 for both x points. Okay. For the parent function, you have 4, 1, 0, 1, 4. And for the dilated function, which has been stretched up, you have 12, 3, 0, 3, and 12, which makes perfect sense because each of these points has been multiplied by 3. It has a factor of 3. So 4 times 3 is 12. 1 times 3 is 3. Okay, all the way through. You can see from these graphs that the sides are getting closer together, but that each of these points is moving further from the x-axis. When we're at 1 on the x-axis, we were at -1, now we're at, when we're at -1 on the x-axis, we were at 1, now we're at 3. Everything is stretching, getting further away. Okay. Here's question number 2 with Daddy Toast. That's scary. It's intense. I can't look at it. Use a table and a graph to show the vertical compression of f of x is equal to 1/3 times the square root of x compared to its parent function, f of x is equal to the square root of x. We know it's a compression because 1/3, the value for k, is a fraction. So it's being sat on, it's being squashed. Pause this, figure it out, come back. Here are your tables. So for x, we have 0, 1, 4, and 9. The 1 didn't work on this one because it's being compressed. Don't stress. It just is what it is. Okay, but the f of x values for the original function, the parent function, are 0, 1, 2, 3. And for the compressed dilated function are 0, 2/3, and 1. And this makes sense because each f of x function is being multiplied by 1/3. So 0 times 1/3 is still 0. 1 times 1/3, this would be 1/3. I don't know why they didn't put that in there, but they chose not to. So this would be 1 and 1/3. 2 times 1/3 is 2/3. 3 times 1/3 is 1. You can see from these graphs that here it's taller, here it's shorter. All of the y points moved closer to the x-axis because they were multiplied by 1/3. All right, here's practice question number 2. This is at the end of the lesson, so write your answer down. Complete the tables to show that y equals kf of x results in the parent function being vertically compressed when k equals 1/2. Okay, pause it, figure it out, come back. Let me find my tools. They went away. Okay, so we know that this is the parent function, this is the compressed function, and that each function is being multiplied by 1/2 or divided by 2, however you prefer to think of it. So 0 times 1/2 is still 0. 1 times 1/2 is 1/2. I'm so good at writing. 16 times 1/2 is 8. It's that easy. Steps to identify the factor k. Compare the equation of the given function and its parent function. Determine the differences. Compare the graph of the given function and its parent function. Determine the differences. Use the results from step 1 and step 2 to identify k and its effect on the parent function. Here's example 1. Use the graph and the equation f of x is equal to 4x squared to identify the vertical stretch k and the effect it has on the parent function f of x is equal to x squared. So first compare the equations. If you look here, you can see that the difference between the two equations is this 4. Therefore, k equals 4. Let's look at the graphs. If you look here, you can see that the graph has been stretched, which means it's a vertical dilation. It's moving up, which means all of these y points are moving further away from the x-axis. So it's stretched further from the x-axis. It has one intercept at 0, 0, and it didn't change in each from one graph to the other. Both are quadratics or parabolas that open upward. The dilated version decreases here and increases faster at a faster rate, has steeper slopes than this one does. Here's example 2. Use the graph and the equation f of x is equal to 1/4 x cubed to identify the scale factor k and the effect it has on the parent function f of x is equal to x cubed. So first compare the equations. You can see the difference between these two equations is this 1/4. Therefore k equals 1/4. If you look at the graphs, you can see that this one has been dilated. It got fatter, it got sat on, it got squished, and that makes sense because this number is a fraction, so therefore it has to be compressed. Therefore, the graph is compressed by a factor of 1/4, and it is closer to the x-axis. Okay, everything got moved closer. When x is 1, it was sitting at y as 1. Now it's sitting at y as 1/4. I can't read it that small. Example 3. Dilate the linear function y equals 3x minus 4 vertically by a factor of k equals 2. Describe the effect the factor of k equals 2 will have on the graph of the function. Well, if we're multiplying everything by 2, it's going to stretch the graph of the function vertically by a factor of 2, right? Because this is a whole number, so it has to go up, it has to stretch. Use a calculator to sketch both functions on this graph. So use the graph calculator, geogebra.com, to graph y equals 3x minus 4. The dilated graph can be entered as y equals 2, because 2 is our k value, times 3x minus 4 in parentheses, as the factor k equals 2 multiplies the entire function. I will show you how to do this because there is one question at the end where you have to be able to graph. Okay, go ahead and start the calculator. And then up here in the input, you're just going to type your formulas. Y equals 3x minus 4, and it went and graphed it for us. And let's do another one. We have y equals 2 times 3x minus 4. Now we have our two graphs right here. Okay? You can see that. Our original one is right here. This is our dilated one, so it got steeper. All right? So describe any changes to the slope. We talked about this. When it got dilated, the slope became steeper. Describe any changes in the y-intercept. So before the y-intercept was at -4, now the y-intercept is going to be lower. You can see that. And describe any changes in the x-intercept. It stayed exactly the same. You can see that right there. Okay. You could figure out what the new y-intercept is because we know that our rate of change is 2. So if our first one was at -4, you just take -4, multiply it by 2, and your new y-intercept is going to be -8. Here's example 4. Dilate the linear function y equals x squared plus 5x plus 6 vertically by a factor of k equals 1/3. Describe the effect the factor of k equals 1/3 will have on the graph of the function. Well, because it's 1/3, we know that it's going to be a compression. Okay. Use a graphing calculator to graph y equals x squared plus 5x plus 6. The dilated graph can be entered as y equals 1/3 times x squared plus 5x plus 6, since the factor k equals 1/3 multiplies the entire function. I'm not going to bother to do that right now. I just showed you how to do it, and you only need to be able to do it once, so don't worry. And then describe any changes in the y-intercept and in the x-intercept. So this is what your two graphs are going to look like. Okay, the y-intercept was multiplied by 1/3. So the original y-intercept is located at 0, 6, clear up here. And the new y-intercept is located at 0, 2. And that makes sense because 6 times 1/3 is 2. Right? The x-intercepts did not change. Both functions have x-intercepts at -3, 0 and -2, 0. Here is example 5. Dilate the square root function y equals negative square root of x minus 3 vertically by a factor of k equals 1/2. Describe the effect the factor k equals 1/2 will have on the graph of the function. Before I go, you should be able to answer this. Is it a stretch or a compression? It's a compression because we're dealing with a fraction. Okay? Then it wants you to go and graph it, which you can do on GeoGebra if you feel the need to. And it wants to know any changes in the y-intercept and the x-intercept. So this is what the graph looks like. The original is orange. The new one is blue. Okay? So the y-intercept, there is no y-intercept, so it's irrelevant. And the x-intercept did not change. Why doesn't the x-intercept change? The x-intercept of a function is the point x, 0. When the function is dilated, each y-coordinate is multiplied by k, creating the dilated point x, k times 0. Since any number multiplied by 0 remains 0, the dilated x-intercept remains at x, 0. So the x-intercept is never going to change. Doesn't matter. You don't have to graph it. If the question is, what happens to the x-intercept? It doesn't change. You don't have to work any harder than that. Here's question number 1 and Daddy Toast. A distance versus time graph illustrates the distance traveled on the y-axis and time traveled on the x-axis. The function y equals 3x models the distances Tracy can run as part of her new half-marathon training plan. What would the new function be if, after training for 3 months, her pace is increased by a factor of 1.5? Word problems are a nightmare. All it wants to know is if you have this formula right here, and you're going to increase it by a factor of 1.5, what's your new formula going to be? Figure it out. Pause the video. Come back. Your new formula is going to be the original formula, which is y equals 3x times 1.5. And then if you simplify it, so 1.5 times 3 is 4.5. Y equals 4.5x. Okay? Now, this is question 2. I didn't change it. Ignore that. 2. How does question 1 relate to vertical compressions and dilations? So what does this mean for vertical compressions and dilations? Now this technically has a fraction in it, but it's above a 1. So is it a compression or a dilation? This situation has an equation that is dilated by a scale factor of 1.5. This means the graph is vertically stretched by a factor of 1.5, making the graph 1.5 times steeper than the original graph. In terms of the situation, Tracy is now 1.5 times faster than when she started her training, which makes sense because when you exercise regularly, you don't get worse, you don't get slower, you don't get weaker, you get better. Here is question number 1, and I had to start adding more pictures because I knew I was going to be struggling by this point. This right here is Seungmin, not In. This is Daddy Toast. Use the graph and the equation f of x is equal to 2 times the cube root of x to identify the vertical stretch k and the effect it has on the graph of the parent function. Note any changes to the intercepts of the original function. So pause the video, go figure it out, come back. Alright, first you compare the equations, the difference between the two equations. The parent function it didn't give you, but the parent function would just be f of x is equal to the cube root of x, okay? So the difference between these two functions is obviously this 2 right here. That means k equals 2. Compare the graphs. If you can see, this is the parent function, this is the dilated function. It got stretched up, which makes sense because it's being multiplied by a whole number, okay? And finally, you have to interpret all this. The graph is stretched by a factor of 2, farther from the x-axis. Both functions have an x and y intercept at the point of 0, 0, which remains unchanged. We already knew that the x-intercept wasn't going to change. In order to figure out the y-intercept, you'd either have to have the tables with all of the y points, or you'd have to have a graph. Okay. Here's question number 2. Use the graph and the equation f of x is equal to 1/2 x squared to identify the vertical shrink or compression factor k and the effect it has on the graph of the parent function. Pause it, figure it out, come back. So first compare the equations. You can see that the original parent equation would be f of x is equal to x squared. So the only difference between these two equations is this fraction 1/2. That means it's being compressed and that the value of k is 1/2. If you compare the graphs, you can see because it's being compressed, it's being squashed down, it's getting fatter, which means all of the y coordinates are moving closer to the x-axis. Okay. Here's practice question number 3. This is at the end of the lesson. Identify the k value for the vertical stretch from the original function, which is orange, to the dilated function, blue. Okay, and it is a stretch because it's getting skinnier. It's getting closer together. So even though it's facing downward, it's still a stretch. Go ahead and pause the video and figure it out. Come back. Okay, this is actually a lot easier than you would think, just like looking at the graph and being like, panic, panic, panic. Look at the formulas. Okay, k value is right there. It's -3. Here's practice question number 4. Identify the factor k for the vertical compression from the original function y equals x plus 6 to the dilated function y equals 1/2 times x the absolute value of x plus 6. Enter your response as a fraction. Speed round, speed round, speed round. What's the difference between these two? Da 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 da. 1/2, so your answer is 1/2. Okay. Here's quick check question number 2. I won't give you the answer, but I'll help you figure it out. The function graphed with the solid orange line is the parent function y equals f of x. Which of the following describes the transformed function y equals 4 f of x, which is shown with a dotted line? So we're going from orange to blue. The parent function has been vertically stretched by a factor of 1/4, or it has been compressed by a factor of 1/4, stretched by a factor of 4, compressed by a factor of 4. So first figure out if it's been stretched or compressed. We're going from orange to blue. And then figure out if the factor is 1/4 or 4. Okay, you should be able to do this because we know that this is the number that we're dealing with. Okay, and we know that if we have a whole number, what is it doing? Is it stretching or compressing? Okay, continuing to the next part of the lesson. Example 1, describe the transformation from the parent function f of x is equal to x squared to the graph of the function f of x is equal to 6x squared. Okay, so the graph is stretched by a factor of 6, which we knew because this is the difference. This is the k value. The y-coordinate of each ordered pair in the transformed graph has increased by a factor of 6, which makes perfect sense because if this y-coordinate is 4, 4 times 6 is now going to become 24, which isn't even showing on this. But 1 times 6 is 6, right? The graph is stretched farther from the x-axis, which is what stretching does. Here's example number 2. Describe the transformation from the parent function f of x is equal to the absolute value of x to the graph of the function f of x is equal to 1/3 times the absolute value of x. So if you look at the graphs, you can see that the dilation is a compression. It's being squashed down and getting fatter by a factor of 1/3. That makes sense. Fractions are compressions. They're getting fatter. The y-coordinate of each ordered pair has decreased by a factor of 1/3. So when we're at an x value of 1 and a y value of 1, it then becomes an x value of 1 and a y value of 1/3, okay? Which would be right there. The graph is compressed closer to the x-axis than its parent function. Example 3. I loved this one so much. I don't know what's going on here. I don't know if a ghost is like choking him. I don't know if he's mad or scared. Whatever. Graph the function f of x is equal to x plus 1 cubed. Then graph the vertically dilated function using the factor k equals 1/2. Because it's 1/2, we know it's going to be a compression. Okay. So if you look at these graphs, you can see that they have the same general shape. They both have the bend. Okay. They have the same x-intercept, which is right here at -1, 0. The dilated function is a vertical compression with a scale factor of 1/2, and y values are closer to the x-axis. Here's example 4, which is all the range of emotions I feel making these videos, except for happy. I don't feel happy, except maybe when I get to stare at stray kids. The graph of the function y equals x minus 2 squared is vertically dilated by a scale factor of 4. What is the effect on the graph? So this formula is shown right here, okay? But we're going to change it by a factor of 4. So the graph would be vertically stretched because 4 is a whole number, so it's going to go up, and would appear narrower, so it's going to be skinnier. Each point would be mapped farther away from the x-axis, so it's going to move further up. 1, 1 would become 1, 4, so it would be clear up here. The x-intercept would not change because the x-intercept never changes, and the new equation would be y equals 4 times x minus 2 squared. All right. Question 1. Describe the transformation from the parent function f of x is equal to the cube root of x to the graph of the function f of x is equal to 4 times the cube root of x. Figure this out, pause it, come back. We know that because this is a whole number, it's going to be a stretch. We know that immediately. The graph is stretched by a factor of 4. The y-coordinate of each pair has increased by a factor of 4. The graph is stretched farther from the x-axis than its parent functions. Here's question 2. Describe how the graph would change if the original function y equals x plus 4 That's not a complete sentence. Good job, people. Be specific and use at least 3 sets of coordinates to illustrate your description. Let me see if I can get more information from the next slide. Okay, from what I can see, it's supposed to be a factor of 1/3. I must have left that out when I was typing, so I apologize. Go ahead and figure this out, pause it, and come back. So the graph would be vertically compressed, and each corresponding point would be closer to the x-axis. The points would go from -7.3 to -7.3 to -7.1. -5, which is right here, -5.1 would become -5.1/3. -4.0 would become -4.0 because the x-axis, the x-intercept never changes. -3.1 would become -3.1/3, and -1.3 would become -1.1. Okay, very end of the lesson. Practice question number 5. Consider the following two functions. F of x is equal to the absolute value of x plus 1, and f of x is equal to 1/2 the absolute value of x plus 1/2. Now this makes me really mad because they haven't done this before, where they changed. I mean, we know this is the k value, but these two changed, and I don't know why they did that. Which option best describes the change from the original to the final function? A vertical stretch, a vertical compression, or no change? Speed round, which is it going to be? If it's a fraction, it has to be a compression. So I don't know why they did this. I guess to try to be jerks, but the answer has to be 2 no matter what. Here's quick check question number 3. Which of the following correctly identifies the factor k for the vertical compression from the function? This is your original function, f of x equals x cubed plus 2, to the function is changing to here. And it wants to know what the value of k is. So don't get distracted by anything else. What is the value of k? And select the correct answer. Ignore this. Ignore this. Here's quick check question number 4. Use a graphing calculator to graph the original function y equals 1/2 x minus 4 and the vertically dilated function with a factor k equals 6. Determine the x-intercepts of both functions. So we need to head back over to GeoGebra. Make sure to clear all the stuff up here so you don't have old graphs screwing this up. We have y equals, we need a fraction, I'm guessing it's this one, 1/2 x minus 4. Okay, there's our first line. And then we need another one, which is going to be y equals, and we know that the factor, that the value for k is 6. So that's going to be the first thing we put in, then everything else needs to go in parentheses. So we have another fraction, 1/2 x minus 4. Okay, this is what your two graphs are going to look like. Okay, if we need to come back here, we will. You can always back up the video because I'm sure it's going to ask us about the x and y intercepts. That seems to be the thing. So our first one is here, so the y-intercept is -4, and the second y-intercept is -24. We'll go see if that's what they want. Okay, it wants to know where the x-intercept is, which I didn't look, so you'll have to back it up, and where the x-intercept is for the next one. So guess what? We didn't need to graph it all the time because the x-intercept doesn't change. We know that. So yeah, figure out the correct answer. Quick check question number 5. Both graphs represent transformations from their respective parent functions. Describe the transformation. Okay, this is your first one. This is your second one. So both graphs represent vertical stretches with the same factors of k. Both graphs represent vertical stretches, although they use different factors of k. Both graphs represent vertical compressions, although they use different factors of k. Both graphs represent vertical compressions with the same factors of k. And to be completely honest with you, this one completely confuses me because we have like an S-bend on this one and we have just like a partial parabola on this one. So hopefully it makes more sense to you than it does to me because I'm very confused. Thank you for existing, Ian.